Testing, testing, 1, 2, 3. Testing, testing. That'll do. Good morning, fancy meat computers. How's everybody doing today? Hope you're doing all right. I see we have a record low of 8 people concurrent with the actual starting of the class. Actually, it's 1 minute past the starting of the class. That's, I should have never said, oh, we jumped up. Nope, that's 8. Okay. I should never have said that the machine learning stuff is not going to be on the exam. Should never have said that. Mistake every time I say it. Anyway. How is everybody? Do we have some people in the chat to say hello? Or is everybody just bots today? There we go. Hi. Thank you for answering. I'm doing okay. Doing pretty okay, I'd say. Yeah. you know, last day of class. So that's exciting. Less exciting for me probably than it is for you, unless you're also taking 1XC3 or 1DM3, one of the courses that's being run in the second half of this summer semester. For some of you, this is the last day of class. No more pencils, no more books, no more teachers, dirty looks, at least until after the exam. You know, it's interesting with the summer courses. We have, like, I have class next Monday for the new class I'm teaching, so it's like, you know, no break at all, just straight into the new course, which is fine. That was kind of how the situation was for this course, actually, going from the winter term into this spring term. I had the exam for the previous offering of 1MD3 the week before. I think it was on a Thursday, and then on Monday I had to start teaching this class. So, very little overlap. Normally they give you like a week to get the exams marked at least, but because they pushed the semester back by a week at the beginning of the semester in January, I hope that's the first and last time that they have that brilliant idea. But yeah, anyway, let's make that a COVID change which is not permanent, shall we? Anyway, so that all being true, looks like we have 12 people here. So why don't we just get started? I hope all of you brought questions for the review period, because that's the thing we're going to be doing once we have finished with machine learning. So, machine learning. We were talking last time about regression models and how regression models can be a manner of accessing machine learning. That is to say, just quickly in review, machine learning in total, in its summation, is it's a set of mathematical techniques that are used to perform various types of data analysis. Machine learning in general is data analysis, usually over large, data sets. So, linear regression, of course, or regression analysis in general, is the attempt to generate a mathematical model based on data points. This is, generally speaking, what machine learning does. We went through the procedure for doing so. This procedure is universally applicable with just a small amount of abstraction to all machine learning, supervised machine learning algorithms. This is the basic idea. So, just to review it quickly, you first obtain your data. You then divide your data into the training set and the testing set. The training set is used to train the machine learning algorithm. The testing set is used to determine how well the machine learning algorithm performs. The division of this data into two sets should be random in order to try to mitigate any bias that might exist in the data based on its position within the dataset. We then, in the case of regression analysis, we run a linear regression or a polynomial regression or whatever type of regression you would like to run. You run the analysis. You then use your analysis to predict y values from x values in the case of linear regression analysis. In the case of generalized machine learning, you would run your machine learning algorithm over your training data. So you would train your algorithm. Then you would use the new data points, the testing data points, you would feed those into the algorithm as well and see what your algorithm predicts the result would be. Normally, this makes sense in the context of something like category analysis or categorization or classification analysis. So if you think back to the example we had with, lizards and snakes and such, whether or not something is a reptile, what you would do is you would feed a new animal, the features of a new animal, into your machine learning algorithm that had been trained, and it would tell you whether it thinks it's a reptile or not. You would, of course, the testing data is still labeled, so you know whether or not the thing is, in fact, a reptile or not. That comes with the data. So you can compare the results that exist inside of the testing set to the result you get from the machine learning algorithm to see how effective your machine learning algorithm is. And that's sort of steps 4 and 5 here. There's another step that's not listed here, which is you would then theoretically then attempt to apply this machine learning algorithm to some kind of real-world setting. If you are a social media company, you would apply your machine learning algorithm would be something like a recommendation system. Recommendation systems are currently a big hotbed of machine learning algorithms. So, when you're watching a video on something like YouTube, YouTube is keeping all kinds of interesting track of all kinds of interesting data. They are keeping track of how what videos you watch, obviously, how long you watch them for, at what points in the video you start and stop watching them. It keeps track of the number of times you watch something. It keeps track of the number of times you go back and forth in the video. It keeps track of all these different things, right? And so essentially, the thing that they say about services on the internet is true. If you're not paying for it, then you are the thing being bought and sold, and data is valuable. So the vast quantities of data that you generate by your mere interactivity with a website like Facebook or YouTube, this is used by these services to try to quote-unquote increase engagement. That's sort of one of the less sinister things that they do with your data, is to try to increase engagement. Although I would argue that probably increasing your engagement with social media is probably not a thing that you want to do anyways. Let's put it this way. It's been documented in various places that social media uses similar techniques to casinos in order to addict people to social media. And, in one sense, it's the worst possible kind it's the worst possible kind of casino, because they've taken your data, right, and the data of people in aggregate, and they have trained these algorithms to spot patterns such that the recommendation system is tuned not only to the general behavior of human beings, but to you specifically, and your behavior within the context of general human beings. So it's And essentially, the modus operandi is to try to keep you on social media as long as possible, to keep you as engaged with social media as as they can possibly get you, which of course means that you know, the time that you would spend doing other things, like actually talking to your friends, or going outside, or exercising, or learning how to cook food, all of these things. These are things that you won't be doing quite so much of because of the addictive quality of social media. So, and it's like I'm not trying to cast moral judgment on it or anything like that. Lord knows I've had my own share of being, sucked into all of these various web services. It's useful to know that that's what's going on, right? If you understand it, then maybe you can be a little bit more intelligent about it, because knowledge is power. But anyway, so let's talk about classification algorithms. Classification algorithms are normally a type of supervised learning. The idea is that we have two or more classes or labels that we are trying to apply to a data set. Think back to our earlier example of a system that's trying to distinguish between photographs of cats and dogs, right? The goal with classification is to come up with a rule that classifies inputs based on the classes in the training data. So whether you're using a clustering analysis to do this, or whether you're using some other, like if you were doing this over images, you would need to introduce some image processing techniques to be able to get the information out of the photograph, right? Because the thing about photographs is it's not obvious to the human what the computer might find to be the most relevant predictor of cat or dog, right? And the computer starts off completely agnostic of what the correct metric is to be watching to see to determine cat or dog, right? It'll look at many different types of analyses, but those types of analyses will be based on existing techniques in image processing. It's not like the computer is going to run out and completely reinvent the entire field of image processing. But anyway, so let's go back to our example data set for animals. So here we go. Column 1 is our animal name. Columns 2 through 6 contain features. And column 7 is the classification. We either have a reptile or we do not. We want to come up with a model that predicts the classification based on the features. So, the first thing that we do is convert each animal's features into a feature vector. We already talked about this somewhat. For our animals, we get the following feature vectors. Rattlesnake is true, 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 0. Dart frog is true, false, 4, etc., etc. Remember what I was saying last class about normalizing these, right? If the way that you're coming up with your classification relies on the magnitude of the difference between these feature vectors, then you probably want to go the extra step of normalizing them so that no particular feature has an undue influence on the outcome of the classification. In fact, it's possible to actually introduce increased or decreased ranges for any one of these features. If you imagine each one of these features having a coefficient, and you increased or decreased the coefficient, you would actually be increasing or decreasing the weighting that feature has in the overall classification. So, in fact, that would be one way that the algorithm might have of training itself, is to because simply knowing the distance may not be sufficient to produce a correct labeling. The algorithm may also need to decide what weight each of these factors has in determining the classification. Maybe it's extremely relevant whether or not the animal has scales, and it is not relevant at all how many legs it has. But anyway, so our classification procedure should be eerily similar to our linear regression procedure. So, number one, we obtain the labeled data. Number two, we construct the feature vectors for the labeled data set. So we plot all of these things. Not plot. We construct these things such that they might be plotted in n-dimensional space. We divide the data set into two sets, a training set and a testing set. We train a classifier on the training data to develop a model. We use the classifier to predict the labels for the testing data, and we measure the accuracy of the predicted labels on the testing data. Are there any questions? Does anybody have any questions at this point in time? Give me a thumbs up if you don't have any questions. Do we have people? Still have 12 people. My goodness, that's a record low. 15 people? That's slightly better. So let's talk just a little bit about how we might go about measuring the accuracy of the predicted labels. So let's imagine that we have only two classifications in this case. Lizard or not lizard, reptile or not reptile. Awesome. Thank you, Boris. There are four possibilities. If we predicted a positive value, and the test value was also positive, thank you, Iris, then we have what is called a true positive result. If we predicted positive and the result was negative, we have a quote-unquote false positive result. If we predicted negative and it was actually positive, we have a false negative. And if we have if we correctly predicted negative, we have a true negative result. The accuracy of the tests is the number that you got true, the number that you either got true positive or true negative out of the total number that you tested. So this might have relevance to everybody's lives right now, because we are. It sort of depends on where in the world you are right now, I think. But for those of us who are still living in Canada, we are still largely living underneath the COVID restrictions that have been in place since Christmas, I think. So part of the entire deal with the COVID, one of the things that's dictating public policy with respect to COVID-19 and the degree to which you're locked down, at least in Ontario, it has to do with the daily case numbers, right? So it's important to understand what daily case numbers actually mean, right? What it means essentially is positive COVID tests, right? So the problem with medical tests is that medical tests are never 100% accurate, right? Take, for example, a test for a cancer. You know, if you have a biopsy to see if you have cancer in your liver or something. There will be a certain percentage of those tests which will be either false negatives or false positives. Generally speaking, with tests, you want to try to avoid, falsity in either of these cases as much as possible. This is why standard procedure in medicine is to not rely solely on one test, right? Normally what would happen is you would have you would have one test that came up with a result, and then you would have further tests to confirm that result, because these tests do not have a 100% accuracy rate. So anyway, sort of drawing this idea back to the idea of the COVID test, if you get the COVID test, you'll get either a positive or a negative result. If you actually do have the cove, and you test as having the cove, that means that you got a true positive result. However, if you test positive but you don't actually have COVID-19, then you have a false positive. Similarly, if you tested negative and you actually did have the virus, then that would be a false negative test. And false tests are not necessarily due to they're not necessarily due exclusively to flaws in the testing process itself. They are sometimes due to flaws in the application of the test process. For example, maybe the nurse didn't stick the cotton swab all the way up your nose, and that might result in a false negative. And if you actually don't have the virus and you didn't test as having the virus, then that would be a true negative result. Of course, the problem is, sort of statistically, we can know roughly what the accuracy of any particular test is, but that doesn't predict the accuracy in any particular case. That's why further tests are typically necessary. So, if you have you could have a test, for instance, that's given to false negatives. Maybe 10% of results are false negatives, right? In that case, if you get a negative result, then you could theoretically have a false negative. But some tests will have a very low false negative rate, but a very high false negative rate, but a very low false positive rate. In that case, you can be sure that something like a positive result will pretty much 100% guarantee that you have the thing, whereas a false negative does not necessarily or a negative result does not necessarily indicate that you don't. Pregnancy tests are like that, actually. A negative on a pregnancy test is not necessarily a negative, for various reasons. But a positive on a pregnancy test pretty much always means that you are pregnant. Anyway, so we will be using the Natural Language Toolkit for classification of text and more general data in Python. So the Natural Language Toolkit is installed on Jupyter Hub. If you want to install it on your own local computer, you can use any of these commands if you know how to do so. If you don't, then it probably comes with Anaconda. And if it doesn't, just look up Natural Language Toolkit and they'll give you a thing to install. So, step 1. Obtain the data from your source. Data should include labels for each data element. It's not labeled data unless the data has labels. For the Natural Language Toolkit, in order to construct a feature vector, we need a list. Each element of the list is a tuple containing two things. Number 1, a dictionary of feature names and values, and B, a label. For example, if we have our animal class, and we have our feature vector, self.features, that'll be our feature vector, we can define a method, features as dictionary, that collects up the feature names, which are predefined. It instantiates an empty dictionary and essentially constructs a dictionary using the feature names and the self.features. It's just formatting it in a manner that the Natural Language Toolkit can accept readily. So, if we instantiate all of these animals, salmon, for example, true, true, false, true, 0, true, this features as dictionary would take the labels, apply them to the feature vector, and you would have a dictionary instead. For example, something like this. The code on the previous slide is a somewhat organized way of generating the following labeled dataset for classification. So we have all of these dictionaries, we have the labels. Notice that we've dropped the name of the animals, names of the animals. We now divide the dataset into two sets, the training and the testing set. Best practice, of course, in the same way as linear regression, is to split the data into two datasets, the training and the testing set, randomly, right? We're taking a random sample, and that is how we are dividing up our data. If we had only one dataset and came up with a model for that dataset, it is not surprising that it would predict that dataset well. The real test is if it can predict another dataset well. So, this is a really small dataset relative to the, relative to the sorts of machine learning algorithms that you would see in the wild. To have like 8 or so data points is vanishingly small. You would probably prefer to have somewhere between 80,000 and 800,000 data points to be able to do something really useful with machine learning. And of course, the laws of statistics apply, because this is fundamentally statistical analysis. So the more data points that you have in your data set, the more accurate your results can become, assuming you haven't baked biases into your model or into your data sets. So, number 4, we can train a classifier on the training data to develop a model. There are many different types of classifiers. We will use, the example used here is called the naive Bayes classifier. So, we have our training data, which is the, feature sets from the beginning of the list to the beginning, 1 minus the beginning of the list. The classifier is nltk.naiveBayesClassifier.train training data. So, this is as easy as it is. You just have to use the method. The fact that all you have to do is use the method in Python is why Python is currently one of the preferred languages for machine learning applications. It's because this is easy in Python. They have put a lot of work into making this easy in Python. Traditionally, artificial intelligence languages, Lisp was the Lisp processor. Lisp, L-I-S-P, was traditionally the language of artificial intelligence. But, you know, it's kind of interesting. Artificial intelligence as a field is, it's kind of an odd duck. Anything that actually becomes successful within the field of artificial intelligence is kind of spun off and produces its own field or subdiscipline is sort of within the software community. It sort of detaches itself from artificial intelligence research as such and becomes its own entity. So you have this process by which artificial intelligence proper gets impoverished by all of its children leaving it alone and empty nesting it over time. And a good example of this was two good examples. Speech. So speech recognition, originally under the auspices of artificial intelligence. I believe the production of speech was originally in that category as well. Image processing, I believe, started off in artificial intelligence as well, and that became its own course in university. But anyway, so, and the same thing is kind of happening to machine learning. Although the origins of it may have been in artificial intelligence, it's machine learning itself is it is now a specific series of techniques, and you know, as time goes on, it becomes more and more refined. So it's sort of become its own subdiscipline, its sub-application, and artificial intelligence research itself is kind of, you know, moving off and continuing in other directions as well. Anyway, so once we've run our training algorithm, we can learn a little bit about the model that it's developed. So, show most informative features. The show most informative features method, will display to you which features this classifier believes to be the most important or informative to the generation of the label. So, legs, turns out legs are pretty relevant. Scales are next most relevant, then cold-blooded, then legs being 0, then egg-laying being true. So, so that's the type of data that it generates. We can then use the classifier to predict the labels for the testing data. We can run the classifier on a feature vector to see what it predicts. So we can create a predictions list for t in testing data. So for every element in the testing data, predictions.append classifier.classify t at 0. T at 0, because remember, the testing data is a series of tuples. The first element of the tuple is a feature vector as a dictionary. The second is the label. We want to classify the feature vector to see if we can match the label. So we give t at 0 to the classifier to classify. We can then measure the accuracy of the predicted label on the testing data using the natural language toolkit.classify.accuracy measurement method. Natural language toolkit has built-in methods for calculating the accuracy, number of correct predictions out of the total number of predictions of the data. So, are there any questions about that? Could we get a thumbs up from the crowd? Because that is classification. Any, how are we doing? Oh, we have 18 people here now. Good. People are just kind of filtering in, eh? Can I get a thumbs up? Yay! Awesome. So much for classification. Sorry. So much for pathos. So, we don't have that much left in machine learning. I imagine we can get it through it in the next 10 minutes. The summary that's not applicable to us this semester. So, we're going to have our, I think we're going to have our review session an hour early, which is good. You guys will have extra time for asking questions. Excellent. So, anyway, sentiment analysis. A special type of classification problem focuses on identifying the quote-unquote sentiment of a piece of text. These are things like happy or positive emotions, negative, sad, angry emotions, frustration, bitterness, ennui, all of the wonderful emotions that are subject to the human character. The basic approach to this is to take the individual words as members of the English language or any other language that you're analyzing and associate them with sentiments. So, you know, if I use the word I have a book here. The book has words in it. If I use the word insatiable, for example, insatiable meaning in the inability to be satiated, I might be, that to me would have a negative connotation. It would be, you know, to say someone or something is insatiable is to say that it cannot be satisfied, which is to express frustration in your inability to satisfy it, or in, you know, the inability to satisfy it. So I would say insatiable might have a general negative affect. So if you go through the dictionary and do this with everything, you get a very, very poor understanding of the English language, at least as it pertains to sentiment. So, once we have labeled individual words as being associated with a particular sentiment, we can then compute a sentiment score for a particular piece of text. The machine learning approach is to label pieces of text as having a particular sentiment and then using classification to predict sentiment. So, you know, if I'm saying, you know, the Maple Leafs, I am sad because the Maple Leafs are out of the playoffs, or I am happy because the Maple Leafs are out of the playoffs, there is, you know, one is happy, the other is sad, because they use the terms happy and sad, right? But you also have to take into account grammar. So it's not, like, if it were as simple as counting up how many happy and sad words you used in a sentence, then we wouldn't, you know, then the computers really would be able to just speak like us, you know? Anyway. So, with respect to sentiment analysis, we use the same familiar procedure. We obtain the labeled data, we construct our feature vectors for the labeled data, which is to say we use natural language processing to construct feature vectors. Incidentally, to a computer scientist, natural language is any language which is commonly spoken by human beings. You have computer languages and you have natural languages. Computer scientists always hold themselves aloof of natural languages because of their imprecision. So you divide your data set into two sets, training set and the testing set. You train a classifier on the training data to develop a model. You apply that model to the testing data and then measure the accuracy of your model. And then you integrate it into whatever tool you're interested in developing this thing for the application of. So, our goal is to transform natural language text into a form that is more efficiently processed. We do this via a process called tokenizing. So we take a piece of text and we split it into words or tokens. Tokenization is actually a step in parsing computer languages as well. But we don't have to get into how compilers work. So, we tag or mark the tokens or words in the passage of text with a tag which represents their grammatical role. So it is known, see dictionaries, whether or not a particular word is a noun, a verb, an adjective, an adverb, a preposition, an article, whatever. Some things have a higher semantic content than others. I believe, it's reasonably easy to speak English without using articles. You don't act like article. I'm not saying that articles are optional. Articles are kind of like, although the amount of semantic content they carry is reasonably low, they're, I would say they're linguistic lubricant. But that's a very engineering way of saying that. So, we then want to stem the words. That is to say, we want to take the words and reduce them to whatever the stem word is for that, for the piece of text. So, this essentially means dropping tenses and cases and gerunds and all that kind of stuff, right? So the words happy, happier, happiest, and happiness all have as their stem word happy, right? So you can reduce all of these words to the idea of happy, because, to say that you are experiencing happiness is the same as to say you are happy. You also want to remove common words that, again, carry little semantic content, such as the, and, but, if, or, was, I, is, me, you. So, conjunctions, prepositions, and articles. We can then construct feature vectors for the labeled data using natural language processing, which, of course, follows the procedure of tokenization, reducing tokens to a root, removing common stop words, constructing a list of all post-processed tokens presented in all samples, and for each sample constructing a feature vector indicating the number of times each word is present in the sample. We can then run classification algorithms on these feature vectors in the same manner as we were doing with lizards. So, Vader is a sentiment analysis tool built into the Natural Language Toolkit. It has already been trained to classify passages of English text on positive or negative sentiment. So, you import nltk.sentiment.vader. Vader is equal to NLTK, or you instantiate sentiment intensity analyzer as Vader. You take a sentence. If you're happy and you know it, clap your hands. You can then print Vader.polarity scores of the sentence. So, this sentence, if you're happy and you know it, clap your hands. 0 negative affect, 0.709 neutral, 0.291 positive, and compound is 0.519. So this is actually mostly a neutral statement rather than a happy statement, although perhaps we can classify it as being happy by noting the lack of negativity. So, and if you think about it, this statement here is primarily an imperative statement, right? It's you're mostly telling someone what to do based on a condition of happiness. So anyway, that I believe is, yep, that's everything. So just a quick reminder to everybody who's listening right now, all 12 of you, 15 of you, 17 of you, ooh. Course evaluations, all right? evals.mcmaster.ca. I would greatly appreciate it if you could let me know how we did this semester. Further to that, yeah, we'll have the break, and then when we come back, we'll have a review session. I think it would work best if we had our review session on Teams rather than on YouTube. That is more typical for that type of format. So I think what I'm going to do is I'm going to end the YouTube lecture here, and we'll meet on Teams in 10 minutes. Okay, guys? All right. Sounds good. All right, I'll see you guys at 10:29. Let's just make it 10:30. Give you guys an extra minute for being so patient.